The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Good morning. Today there is a bit of an overview on the iCub robot, and it will be about one hour and a half. And we have organized the schedule for this time in a series of 4 small talks and then a demo from the iCub, a live demo. So I will give you an overview of the kind of skills and capabilities that the iCub has developed so far, while Alessandro, Rafaello, and Guilia will show you a bit what's going on right now on the iCub, part of what's going on the robot. So they're going to talk about their recent work. So let's start with the presentation. This is iCub, which is a child humanoid robot, given its size. And the project of the iCub started in 2004. And the iCub, actually the iCubs, because there are many of them, they are built in Genova at the Italian Institute of Technology. And the main motivation behind the creation, the design of this platform was to actually have an autonomous, it was a way to have a platform in order to study how intelligence, how cognition emerges in artificial embodied systems. So Giulio Sandini and Giorgio Metto, that you consider, are the actual original founders of the old iCub world. So they are both directors at the IIT. And this is a bit of a timeline that I drew. Actually, there are many other things going on during all these 11 years. This is a video celebrating the actual first 10 years of the project. And actually, you can see many more things that the iCub will be able to. But I selected this part because I think they could be useful also if you are interested in doing projects with a robot, to have an idea of the kind of skills and the kind of feedback that the robot can provide you to do experiments. So, as I told you, iCub was built with the idea of replicating, in some sense, an artificial embodied system that could explore the environment and learn from it. So it has many different sensors. These are some of them. So in the head, we have one accelerometer and the gyroscope in order to provide inertial feedback to the system, and 2 Dragonfly cameras that provide medium resolution images. And as you can see, there is it's all about 1 meter and something, and it's pretty light, 25 kilograms, and has lots of degrees of freedom. So 53 degrees of freedom, and they allowed the robot to perform many complex actions. It's provided with torque and 4 sensors, and I go over these in a minute, and also his whole body, or at least the cover part of the robot, the black parts that you can see there, are all covered in artificial skin, so they provide feedback about contact with the external world. And it has also microphones mounted on the head, but probably for sound and speech recognition, it's better to use direct microphone feedback at the moment because of course, noise cancelling problems and so on. So if you're interested into speech and sound feedback, we are going to use other kind of microphones. So during these 11 years, iCub has been involved in many projects, and indeed part of what I'm going to show you is the result of the joint effort of many labs, mainly in Europe. These are mostly European projects, but iCub is also is an international partner of the CBMM project. Center. So regarding force-torque sensors, they are these sensors that you can see there.
So they provide the feedback about external and internal forces for the robot, and also torques. So forces are on these axes and torques around. And they're mounted in each of the limbs of the robot and the torso, and they allow the robot to feel how the intensity
of its interaction with the world. And indeed, with this kind of object, you can do many different things. So for instance, in this video, I'm showing an example of how the feedback provided by the force torque sensor can be used to guide the robot and teach it to learn different kind of actions, like in this case, a pouring action, and then repeat it and maybe try to generalize it. So force torque sensors provide the robot feedback about the intensity of the interaction with the external world, but they they're not allowed to have the robot have an idea of where this kind of interaction is occurring. So for this, we have artificial skin covering the robot, as I told you, and the technology used for this kind of skin that you can see here for the palm of the end of the robot is capacitive, and it's similar to the technology used for cell phone, for smartphone, and it is basically it's using, if you can see these yellow dots, they are all electrodes that together with another armor they form a capacitor, and therefore let's say the way the armors of this capacitor are deformed when there is an interaction with the environment allow to provide the feedback of the kind of intensity of the pressure that is occurring in different areas, and of course the location itself is providing the information about where this interaction is occurring. And artificial skin, it's actually really useful for an embodied agent, and for instance, like you can see in this video, without using this feedback, if you have a very light object, the robot is not able to detect the fact that it is interacting with something. It's just closing the end, and since it doesn't have any feedback, it's crushing the object. While by using the sensors on the fingertips of the hand, the robot is able to detect that it's actually touching something, and therefore is stopping its action without crushing the object. So other useful things that can be done with artificial skin. So this is an example of combining the information from the force torque sensor and the artificial skin. So the artificial skin allows to detect where and a bit the direction of the kind of force that is applied to the robot. And in this case, the robot is counterbalancing is negating the effect of gravity and of internal forces. So it's basically having its arm floating around like if it was in space, and there is no friction. So by touching the arm of the robot, we have the arm drifting in the direction opposed to where the force is applied, or the torque. As you can see, sometimes the arm is turning, but as you can see, it drifts like if it was in space without any friction, because exactly it's negating both gravity and internal forces. So, and finally, again about artificial skin, this is some work by Alessandro, but he's going to talk about something else, but I found this particularly interesting to show. So this is an example of the robot self-calibrating its own model, or the model of its own body with respect to its own hands. So the idea is to have the robot use the tactile feedback from the fingertips and the skin of its forearm, for instance, to learn the relation that exists, the position that there exists between the fingertip and the arm, and therefore it's able first by touching itself to learn this correspondence, and then to actually show that it has learned this kind of correlation by reaching that point when someone else touches the same point and it tries to reach it. And therefore, this can be seen as a way of self-calibrating without the need of a model of the kinematics of the robot. The robot would just be able to explore itself and learn how different parts of its body relate one to the other. And again, related to self-calibration in some sense, but this is more of a calibration between vision and motor activity. This is a work appeared in 2014, in which basically the the correlation between the kind of actions that the robot is able to perform is calibrated with respect to its ability to see the world, to perceive the world. So in this kind of video that I'm going to show, the robot is trying to reach for an object, and it's failing in its action because the actual model of the world that is used to perform the reaching is not aligned with the 3D model provided by vision. And this can happen due to small errors in the kinematics or in the vision, and therefore even just small errors cause a complete failure of the system. And therefore, by trying to correlate the two information, the one from the kinematics, so in this case, the robot is using its own fingertip to see where actually its hand is in the image, and when the kinematic model predicts the hand should be. So the green dot is the point predicted by kinematics, so where the system expects the fingertip to be and where actually the fingertip is. So of course, by learning these relations, the robot is able to cope with this kind of misalignment, and therefore, after a first calibration phase, it's able to perform the reaching action successfully. So as you will see in a moment. So also this kind of ability of self-calibrating would be pretty useful in case also of situations in which the robot is damaged, and therefore its actual model changes completely. And yeah, as you can see, now it's reaching and it's performing the grasp correctly. Okay. So finally, before going with the actual talks, I'm going to show a final video about balancing. Some of you have asked us if the robot walks, and the robot is currently not able to walk, but this is a video from the people from the group that is actually in charge of making the robot walk, and the first step, of course, will be balancing, and this is an example of it. So it's actually a one-foot balancing where multiple components of the skills of what I've shown you about the iCub, so force and torque sensing, inertial sensing, are combined together to have the robot stand on one foot, and also be able to cope with the interaction external forces that could try to make it to have it fall. So yeah, there is here, yeah. They are applying forces to the robot, and it's still able to detect the forces, to cope a bit with the forces, but to stay stable. Okay, so this was just a brief overview of some things that can be done with the iCub, and actually the next talk will be a bit more about what's going on with it. So I guess this is it. Yeah.
I wanted to talk to you about part of my PhD project that was about tackling the perception problem. Oh, sorry, there is some sound coming out. Okay. Tackling the perception problem through the use of multisensory integration. And specifically, I narrowed down this big problem by implementing a model of peripersonal space on the iCub. That is a beer-inspired approach. Peripersonal space is a concept that has been studied in neuroscience and psychology for years. And so let me start with what peripersonal space is and why it is so important for humans and animals. It is defined as the space around us within which objects can be grasped and manipulated. It's an interface, basically, between our body and the external world. And for this reason, it benefits from a multimodal integrated representation that merges information between different modalities. And historically, these have been the vision system, the tactile system, the proprioception, auditory system, and even the motor system. Historically, it has been studied by two different fields: the neurophysiology on one side, and all the disciplines related to psychology and developmental psychology on the other. They basically followed two different approaches, the former being bottom-up, the latter being top-down, and they came out with different outcomes. The former emphasizes the role of the proprioception and its interplay with the motor system in the control of movements, whereas the latter was focusing mainly on the multisensory aspect, that is, how different modalities were combined together in order to form a coherent view of the body and the nearby space. Luckily, in the recent years, they started to converge to a common ground and a shared interpretation. And for the purposes of my work, I would like to highlight three main aspects. Firstly, and this one is, might be of interest from an engineering perspective, peripersonal space is made of different reference frames that are located in different regions of the brain. And there might be a way for the brain to switch from one to another according to different contexts and goals. And secondly, as I was saying, peripersonal space benefits from a multisensory integration in order to form a coherent view of the body and the surrounding space. In this experiment made by Fogassi in 1996, they basically found a number of so-called visuotactile neurons that are a set of neurons that fire both if stimulated in a specific skin part and if an object is presented in the surrounding space. So this means that these neurons encode both the visual information and the tactile information, but they also have some proprioceptive information because they are basically attached to the body part they belong to. Lastly, one of the main properties of this representation is intrinsic plasticity. And for example, in this experiment made by Iariki 10 years ago, the extension of these receptive fields in the visual space, so in the surrounding space, after training with the rake, have been shown to go up to enclose the tool, as if this tool becomes part of the body. So through experience and through tool use, the monkey was able to grow this receptive field. Okay, and in robotics, I mean, those are properties that are very nice, and we would like them to be available for the robot. And in general, in robotics, works related to peripersonal space can be divided into two groups. On the one side, there are the models and the simulations, basically. The closest one to my work was the one from Fouquet and colleagues that are from Azada's lab, in which they used a simulated robot in order to model the mechanisms that are leading to this visuotactile representation. On the other side, there are the engineering approaches that are few. The closest one is this one by Mittendorfer from Gordon Cheng's lab, in which they firstly developed a multimodal skin, so they developed the hardware available to do that, and then they used it in order to trigger local avoidance responses, some reflexes to incoming objects, let's say. We are trying to position ourselves in the middle. Let's say we are not trying to create a perfect model of peripersonal space from a biological perspective, but on the other side, we would like to have something that is also working on the real robot and useful for our purposes. So from now on, I will divide this presentation in two parts. The first one will be about the model itself, so what we think would be useful for tackling the problem. On the other side, I will show you an application of this model that is basically using this local representation in order to trigger avoidance responses or reaching responses distributed throughout the body. And so let me start with this, the proposed model of peripersonal space. Loosely inspired by the neurophysiological findings I discussed before, we developed this peripersonal space representation by means of a set of spatial receptive fields that were going out from the robot's skin. So basically, they were extending the tactile domain into nearby space. Each tactile, that is, each patch the iCub skin is composed of, will experience a set of multisensory events. So basically, we were training we were letting the robot learn these visuotactile associations by taking an object and making it contact on the skin part. And it will learn, thanks to this experience, it will learn a sort of probability of being touched, basically a prior to contact activation, when a new incoming object is presented. To this end, we basically created this cone-shaped receptive field that is going out from each of the tactiles. And for any object that is entering this receptive field, we record a buffer of 3 seconds in the past. So basically the idea is that the robot has some information from what was going on before the touch, the actual contact. And if this object eventually ends up touching the tactile, this will be, let's say, labeled as a positive event that will enforce the probability of a similar event ending up touching the tactile. If not, for example, it might be that the object enters this receptive field and at the end ends up touching another tactile. This will be labeled as negative. So at the end, we will have a set of positive and negative events the tactile can learn from. This is a 3-dimensional space because the distance is 3-dimensional, and we narrowed it down to a 1-dimensional domain by basically taking the norm of the distance, but also the relative position of the object and the tactile in order for us to be able to cope with calibration errors that were amounting up to a couple of centimeters, so were significant. And so this one-dimensional variable has been discretized in a set of bins, and for each bin we computed the probability of an event belonging to that bin of being touched. So the idea is that at 20 centimeters the probability of being touched will be lower than at 0 centimeter. This is the intuitive idea. And over this one-dimensional binarization, we use the pattern window interpolation technique in order to provide us with this 2-dimensional function that at the end will give us an activation value that is proportional with the distance of the object. So as soon as a new object will enter the receptive field, I will have the tactile that will fire before being contacted, touched. We did basically 2 experiments. Initially, we did a simulation on MATLAB in order to assess the convergence on the long-term learning, the one-shot learning behavior, to assess if our model was able to cope with noise, with different calibration errors. And then we went on the real robot. We presented the robot with different objects, and we were basically touching the robot for 100 times in order to make it learn these representations. So trust me, I don't want to bother you with this kind of technicalities, but we did a lot of work to assess. This is basically the MATLAB result. And so let me go on the second part, in which the robot, the main problem was for the robot to detect the object visually. In order for us to do that, we developed a 3D tracking algorithm that was able to track arbitrary objects, basically. To this end, we used some software that was already available in the iCub software repository that in general provides you with some basic algorithms that you can play with. And namely, we used a 2-dimensional optical flow made by Carlo, and a 2D particle filter, and a 3D stereo vision algorithm that is basically the same as I was showing before during the action recognition game. And this basically was feeding a 3D Kalman filter in order to provide us with a robust estimation of the 3D position of the object. So the idea is that the motion detected from the optical flow acts as a trigger for the subsequent pipeline, in which basically after a consistent enough motion in this optical flow module, this will be a template that starts to be tagged in the 2D visual world by this. And then this information is sent to the 3D depth map, and this will be feeding the Kalman filter in order to provide us with this stable representation, because obviously the stereo system doesn't work that good in our context. And this, if it works, no, yeah, Okay. On my laptop it works good. Okay, now it works. Okay, this is the idea. So I was basically moving the object in the beginning, whatever object it is, it's okay. Then when it is detected, this pipeline starts, and you can see here the tracking. This is the stereo vision. This is the final outcome. This was used for the learning. We did a lot of iterations of these objects that were pushing the skin on different body parts. This is the graph. I don't want to talk about that, so let me start with the video. This is basically the skin, and this is the pipeline I was showing before. When there is a contact, there is a red activation here. You can see here the red activation. And soon after, since this thing works also with one example, the tactile starts firing before the contact. And obviously, this is improved over the time, and it depends on the body part that is touched. For example, if I touch here, I'm coming from the top, so the representation starts firing mainly here. And this obviously depends on the specific body part. Now I think that I'm going to touch the hand, and so after a while, I will have an activation of the hand. Obviously, I will have also some activation of the forearm because I was getting closer to the forearm. And as an application of this one is basically simply a representation, so it's not that useful. We basically exploited it in order to develop an avoidance, a margin of safety around the body. Let's say if the tactile is firing, I would like it to go away from the object, assuming that this can be a potentially harmful object. And on the other way, I would like it to be able to reach with any body part the object under consideration. So to this end, we developed an avoidance and catching controller that was able to leverage on this distributed information and perform a sensory-based guidance of the motor actions by means of these visual tactile associations. And this is basically how it works. So this is at the testing stage, so I already learned the representation. As soon as I get closer, the tactile starts firing because of the probabilities I was learning, and the arm goes away. Obviously, the movement depends on the specific skin part that has been touched. If I'm touching here, the object will go away from here. If I'm touching if I'm coming from the top, I think this one was doing from the top. Yes, the robot will go away in this direction. No, from the back. The robot will go away from another direction. And the idea here is not to explicitly tackle the problem from a classical robotics approach, but basically this behavior emerges from the learning. And the idea was very simple. We were basically looking at the tactile that were firing. If they were firing enough, we were recording their position, and we were doing basically a population coding that is a weighted average according to their activation and their position. We did that both for the position of the tactile and the normal. So at the end, if we have a bunch of tactiles here, we will end up with 1 point to go away from. And on the other side, the catching, the reaching was basically the same, but in the opposite direction. So if I want to avoid, I do this. If I want to catch, I do this. Obviously, if you do it in the hand, this will be a standard reaching, robotic reaching, but this actually can be triggered also in different body parts. As you can see here, I get a virtual activation and then a physical contact. And yes, basically our design was to do to use the same controller for both of the behaviors. So these are this is also some technicalities that I don't want to show you. So in conclusion, the architecture presented here is, to our knowledge, the first attempt at creating a decentralized multisensory visual tactile representation for a robot and its nearby space by means of the distributed skin and its interaction with the environment. One of the assets of our representation is that learning is fast. As you were saying, it can learn also from one single example. it's in parallel to, for the whole body, in the sense that every tactile learns independently its own representation, and it's incremental, in the sense that it converges toward a stable representation over the time. And importantly, it is adapted from experience. And so basically, it can automatically compensate for errors in the model, that for humanoid robots is one of the main problems when merging different modalities. Okay, thank you. If you have any question, feel free to ask.
And I'm Rafaello, and today I'll talk to you about a little bit of my work on machine learning and robotics. In particular, some subsets of machine learning, which are large-scale learning and incremental learning. But what do we expect from a modern robot, and how can machine learning help out with this? Well, we expect modern robots to work in particularly unstructured environments, which they have never seen before, and to learn new tasks on the fly depending on the particular needs throughout the operation of the robot itself, and across different modalities, for instance, vision, of course, but also tactile sensing, which is available on the iCub, and also proprioceptive sensing, including force sensing, kinematics, and so on and so forth. And we want to do all of this throughout a very long time span, potentially, because we expect robots to be companions of humans in the real world, operating for maybe years or more. And this poses a lot of challenges, especially from the computational point of view. And machine learning can actually help with this, tackling these challenges. For instance, there are large-scale learning methods which enable, which are algorithms which can work with very large-scale data sets. For instance, if we have millions of points gathered by the robot cameras throughout 10 days, and we want to process them, well, if we use standard machine learning methods, that will be a very difficult problem to solve if we don't use, for instance, randomized methods and so on and so forth. We also want, machine learning also has incremental algorithms, which can allow the learned model to be updated as new, previously unseen features are presented to the agent. And also, there is a subfield of transfer learning, which allows knowledge learned for a particular task to be used for solving another related task without the need for seeing many new examples for the new task. So my main research focuses are especially in machine learning. I work especially in large-scale learning methods, incremental learning, and in the design of algorithms which allow for computational and accuracy trade-off. I will explain this a bit more later. And as concerns robotics applications, I work with Guilia, Carlo, and others on incremental object recognition. So in a setting in which the robot is presented new objects throughout a long time span, and it has to learn them on the fly. And also I'm working in a more I'm working in a system identification setting, which I will explain later, related to the motion of the robot. So this is one of the works which has occupied my last year, and it is related to large-scale learning. So if we consider that we may have a very large N, which is the number of examples we have access to, And if in the setting of kernel methods, we may have to store a huge matrix, the matrix K, which is n by n, which could be simply impossible to store. So there are randomized methods like the Nystrom method, which enable to compute a low-rank approximation of the kernel matrix simply by drawing few points m at random, few examples m at random, and building the matrix K and M, which is much smaller because M is much smaller than N. And this is a well-known method in machine learning, but we tried to see it from a different point of view than usual. Usually this is seen just from a computational point of view in order to fit a difficult problem inside limited computers with limited capabilities, while we proposed to see the Nystrom approximation as a regularization operation itself. So if we consider the usual way to in which the Nystrom method is applied, for instance, with the kernel regularized squares, the parameter m, so the number of examples we are taking at random, is usually taken as large as possible in order just to fit the memory of the available machines. While actually, after choosing a large M, it is often necessary to regularize with Tikhonov regularization, for instance. And this sounds a bit like a waste of time and memory, because actually what regularization, roughly speaking, does is to discard the irrelevant eigencomponents of the kernel matrix. So we observe that we can do this by just picking less random examples, and so having a smaller model which can be computed more efficiently and without having to regularize again later. So M, so the number of examples which are used, controls both the regularization and the computational complexity of our algorithm. This is very useful in a robotics setting in which we have to deal with lots of data. As regards the incremental object recognition task, this is another project I'm working on. And imagine that the robot has to work in an unknown environment, and it is presented novel objects on the fly, and it has to update its object recognition model in an efficient way without retraining from scratch every time a new object arrives. So this can be done easily by a slight modification of the regularized least squares algorithm and proper reweighting. An open question is how to change the regularization as n grows, because we didn't find yet a way to efficiently update the regularization parameter in this case. So we are still working on this. The last project I'll talk about is more related to, let's say, physics and motion. So we have an arbitrary limb of the robot, for instance, the arm, and our task is to learn a model which can provide an inverse dynamics model, so which can predict the inner forces of the arm during motion. This is useful, for instance, in contact detection setting. So when the sensor readings are different from the predicted one, that means that there may be a contact. Or for external force estimation, or for example for the identification of the mass of a manipulated object. So we had some challenges for this project. We had to devise a model which could be interpretable, so in which the rigid body dynamics parameters would be understandable and intelligible for control purposes. And we wanted this model to be more accurate than standard multi-body dynamics, rigid body dynamics model. And also we wanted it to adapt to changing conditions throughout time. For instance, during the operation of the robot, after 1 hour, the changes in the temperature determine change also in the dynamic properties of the mechanical properties of the arm, and we want to accommodate for this in an incremental way. And so this is what we did. We implemented a semi-parametric model in which the first part, which has priority, is a simple incremental parametric model, and then we use random features for building a non-parametric incremental model which can be updated in an efficient way. And we've shown with several experiments that the semi-parametric model works as well as the non-parametric one, but it's faster to converge because it has an initial knowledge about the physics of the arm. And it is also better than the fully parametric one because it also models, for example, dynamical effects due to the flexibility of the bodies and dynamic effects which are usually not modeled by rigid body dynamics models. Okay. Another thing I'm doing is maintaining the Grand Unified Regularized Least Squares library, which is a library for regularized least squares, of course. It supports a large-scale dataset. It was developed in joint creation between MIT and IIT some years ago, and by others, not by me. And it has a MATLAB and a C++ interface. If you want to have a look at how these methods work, I suggest you to try our tutorials, which are available on GitHub.
I'm Giulia, and I work on the iCub robot with my colleagues, especially on vision, and in particular on visual recognition. I work under the supervision of Lorenzo Natale and Lorenzo Rosasco, who both will be here for a few days in the following weeks. And the work that I'm going to present has been done in collaboration with Carlo and also Francesca Odone from the University of Genova. So, in the last couple of years, computer vision methods based on deep convolutional neural networks have achieved remarkable performance in tasks such as large-scale image classification and retrieval. And the extreme success of these methods is mainly due to the increasing availability of always larger data sets, and in particular I'm referring to the ImageNet-1, which is composed by millions of examples labeled into thousands of categories through crowdsourcing methods such as the Amazon Turk. And in particular, the increased data availability together with the increased computational power has allowed to train deep networks characterized by millions of parameters in a supervised way from the image up to the final label through the backpropagation algorithm. And this has allowed to mark a breakthrough, in particular in 2012, when Alex Krzyzewski proposed for the first time a network of this kind trained on the ImageNet dataset, and definitely won the ImageNet large-scale visual recognition challenge in this way. And the trend has been confirmed in the following years, so that nowadays problems such as large-scale image classification or detection are usually tackled following this deep learning approach. And not only, it has been also demonstrated, at least empirically. Oh, I'm sorry that maybe this is not particularly clear, but that this is the Krzyzewski network. Models of networks of this kind trained on large data sets, such as the ImageNet 1, do provide also very good general and powerful image descriptors to be applied also on other tasks and data sets. In particular, it is possible to use a convolutional neural network trained on the ImageNet dataset, feed it with images, and using it as a black box, extracting the vectorial representation of the incoming images as the output of one of the intermediate layers. Or even better, it is possible to start from a network model trained on the ImageNet dataset and fine-tune its parameters on a new dataset for a new task, and achieving and surpassing the state-of-the-art, for example, also on the Pasquale dataset and other tasks, following this approach. So, it is natural to ask at this point why, instead in robotics, providing robots with robust and accurate visual recognition capabilities in the real world is still one of the greatest challenges that prevents use of autonomous agents for concrete applications. And actually, this is a problem that is not only related to the iCub platform, but it is also a limiting factor that affects the performance of latest robotics platforms, such as the ones that have been participating, for example, to the DARPA Robotics Challenge. Indeed, as you can see here, robots are still either highly teleoperated or complex methods to, for example, map the 3D structure of the environment and label it a priori must be implemented in order to enable autonomous agents to act in very controlled environments. So we decided to focus on very simple settings where, in principle, computer vision methods, as the ones that I've been describing you, should be at least, well, should provide very good performances, because here the setting is pretty simple. And we try to evaluate the performance of these deep learning methods in these settings. Here you can see the robot, that one, standing in front of a table. There is a human which gives verbal instruction to the robot, and also, for example, in this case, the label of the object to be either learned or recognized. And the robot can focus his attention on potential objects through bottom-up segmentation techniques. For example, in this case, color or other saliency-based segmentation methods. I'm not going into the detail of this setting because you will see a demo after my talk of this. Another setting that we are considering is similar to the previous one, but this time there is a human standing in front of the robot and there is no table, and the human is holding the objects in his hands and showing one object after the other to the robot providing the verbal annotation for that object. The robot, in this way, for example here, can exploit motion detection techniques in order to localize the object in the visual field and focus on it. The robot tracks the object continuously, acquiring in this way cropped frames around the object that are the training examples that will be used to learn the object's appearance. So, in general, this is the recognition pipeline that is implemented to perform both the two behaviors that I've been showing you. As you can see, the input is the image, the stream of images from one of the two cameras. Then there is the verbal supervision of the teacher. Then there are segmentation techniques in order to crop a region of interest from the incoming frame and feed this crop to a convolutional neural network. In this case, we are using the famous Krzyzewski model. Then we encode each incoming crop in a vector as the output of one of the latest layers of the network. And we feed all these vectors to a linear classifier, which is linear because in principle the representation that we are extracting is good enough for the discrimination that we want to perform. And so the classifier uses these incoming vectors either as examples to be either as examples for the training set or assigns to each vector the prediction, the prediction label. And the output is an histogram with the probabilities of all the classes, and the final outcome is the one with the highest probability. And the histogram is updated in real time. So this pipeline can be used either for one or the other settings that have been described you. So in particular, we started from trying to list some requirements that, according to us, are fundamental in order to implement a sort of ideal robotic visual recognition system. And these requirements are usually not considered by typical computer vision methods as the ones that have been described you, but are the same fundamental if we want to achieve human level performances in the settings that I've been showing you. For example, first of all, the system should be, as you have seen, as much as possible self-supervised, meaning that there must be techniques in order to focus the robot's attention on the objects of interest and isolate them from the visual field. Then, hopefully, we would like to come out with a system that is reliable and robust to the variations in the environment and also in the object's appearance. Then, also, as we are in the real world, we would like a system able to exploit the contextual information that is available. For example, the fact that we are actually dealing with videos, so the frames are temporally correlated, and we are not dealing with images in the wild as the ImageNet case. And finally, as Rafaello was mentioning, we would like to have a system that is able to learn incrementally to build always richer models of the object through time. So we decided to evaluate this recognition pipeline according to the criteria that have been described to you. And in order to provide reproducibility to our study, we decided to acquire a dataset on which to perform our analysis. However, we would like also to be confident enough that the result that we obtain on our benchmark will hold also in the real usage of our system. And this is the reason why we decided to acquire our dataset in the same application setting where the robot usually operates. So this is the iCub World 28 dataset that I acquired last year. as you can see, is composed by 28 objects divided into 7 categories and 4 instances per category. And I acquired it for 4 different days in order to test also incremental learning capabilities. The dataset is available on the IIT website, and you can also use it, for example, for the project of Trust 5, if you are interested. And this is an example of the kind of videos that I acquired, considering one of the 28 objects. There are 4 videos for the train, 4 for the test, acquired in 4 different conditions. The object is undergoing random transformations, mainly limited to 3D rotations. And as you can see, the difference between the days is mainly limited to the fact that we are just changing the conditions in the environment, for example, the background or the lighting conditions. And we acquired 8 videos for each of the 28 objects that I showed you. So first of all, we tried to find a measure, as I was saying before, to quantify the confidence with which we can expect that the results and the performance that we observe on this benchmark will also hold in the real usage of the system. And to do this, first of all, we focused only on object identification for the moment, so the task is to discriminate the specific instances of objects among the pool of 28. And we decided to estimate for an increasing number of objects to be discriminated from 2 to 28, the empirical probability distribution of the identification accuracy that we can observe statistically for a fixed number of objects that is depicted here in the form of box plots. And also we estimated for each fixed number of objects to be discriminated the minimum accuracy that we can expect to achieve within increasing confidence levels. And this is a sort of data sheet. The idea is to provide an idea to an hypothetical user of the robot of the identification accuracy that can be expected given a certain pool of objects to be discriminated. So the second point that I'll briefly describe you is the fact that we investigated the effect of having a more or less precise segmentation in the image. So we evaluated the task of identifying the 28 objects with different levels of segmentation, starting from the whole image up to a very precise manual segmentation of the objects. It can be seen that indeed, even if in principle these convolutional networks are trained to classify objects in the whole image as it is in the ImageNet dataset, it is still true that in our case we observe that there is still a large benefit from having a fine-grained segmentation. So probably the network is not able to completely discard the non-relevant information that is in the background. So this is a possible interesting directions of research. And finally, the last point that I decided to tell you, I will skip on the incremental part because it's still an ongoing work that I'm doing with Rafaello, is about the exploitation of the temporal contextual information. Here you can see the same kind of plot that I showed you before. So the task is object identification, increasing number of objects, and the dot black line represent the accuracy that you obtain if you consider, as you were asking before, the classification of each frame independently. So you can see that in this case the accuracy that you get is pretty low, considering that we have to discriminate between only 28 objects. However, it is also true that as soon as you start considering instead of the prediction given looking only at the current frame. The most frequent prediction occurred in a temporal window, so in the previous, let's say, 50 frames. You can boost your recognition accuracy a lot, as you can see here, from green to red. Increasing the length of the temporal window increases the recognition accuracy that you get. This is a very simple approach, but it is showing that actually it is relevant, the fact that we are actually dealing with videos instead of images in the wild. And it is another directions of research. So finally, in the last part of my talk, I would like to tell you about the work that I'm actually doing now, which is concerning about most object categorization tasks instead of identification. And this is the reason why we decided to acquire a new dataset, which is larger than the previous ones, because it is composed not only by more categories, but in particular by more instances per category, in order to be able to perform categorization experiments, as I told you. Here you can see the categories with which we are starting are 28, divided into 7 macro categories, let's say. But the idea of this dataset is to have a continuously expandable in time dataset. So there is an application that we used to acquire this dataset, and the idea is to perform periodical acquisitions in order to incrementally enrich the knowledge of the robot about the objects in the scene. Also, another important factor regarding this dataset is that differently from the previous one, this will be divided and tagged by nuisance factors. And in particular, for each object, we are acquiring different videos where we isolate the different transformations that the object is undergoing. So we have a video where the object is just at different scales, then it is rotating on the plane, outside the plane, it is translating, and then there is a final video where all of these transformations occur simultaneously. And finally, to acquire this dataset, we decided to use the depth information, so that in the end we acquired both the left and the right cameras, and in principle this information could be used to obtain the 3D structure of the objects. And this is the idea that we used in order to make the robot focusing on the object of interest using disparity. Disparity is very useful in this case because it allows to detect unknown objects, just given the fact that we know that we want the robot focused on the closest object in the scene. So it is a very powerful method in order to have the robot tracking unknown objects with all different lighting conditions and so on. And yeah, here you can see this is the left camera, this is the disparity map, this is its segmentation, which provides an approximate region of interest around the object, and this is the final output. So I started acquiring the first, it should be red, but it's not very clear. I mean, I started acquiring the first 5 categories among these 21 listed here, which are the squeezer, the sprayer, the cream, the oven glove, and the bottle. For each row, you see the 10 instances that I collected. And the idea is to continue acquiring them when I come back in Genova. And so here you can see an example of the 5 videos. Actually, I acquired 10 videos per object, 5 for the training set and 5 for the test set. And you can see that in the different videos, the object is undergoing different transformations. And this is the final one, while all these transformations are mixed. Oh, these are the images here are not segmented yet, so you can see the whole image, but in the end, also the information about the segmentation and disparity and so on will be available. And this data set regarding the 50 objects that I acquired, together with the application that I'm using to acquire the data set, are available if you are willing to use them for the projects in Trust 5, for example, in order to investigate the invariant properties of the different representations. And so, that's it.